Today is January 23rd, and this is the hard daily integral for today. So let's start. First, notice that we have the floor function right here. So let's see when this floor function is actually constant. So let's say we go from 1 to 2 and we don't include 2, then the floor of x is going to be 1. So if x is from 1 to 2, where we don't include 2, the floor of x is 1. If we go from 2 to 3, we have the floor of x is equal to 2. So like this, if we go from n to n plus 1, we know that the floor of x is equal to n. So like this, we'll partition our integral into parts. And this way to it. Let's go from n equals 1 to infinity. So we'll go from n to n plus 1. So this is basically saying the integral from 1 to 2, and the integral from 2 to 3, and we are adding all these integrals. And we have pi sine of pi x over 2n dx. Now we can factor out the 1 over 2n, the sum from n equals 1 to infinity, the integral of n to n plus 1 pi sine of pi x dx. So here, notice that we have pi sine of pi x. Well, it's very easy to tell that if we do a substitution t, this pi will be gone and we'll only have sine of t. So our integral is going to be negative cosine of pi x. So we have the sum from n equals 1 to infinity, 1 over 2n. We have negative cosine of pi x from n to n plus 1. So now we have the sum from n equals 1 to infinity, 1 over 2n. We have now cosine of n pi x, minus cosine of n pi plus n. Sorry, x, why do we have an x? We do not need any x's. We have n pi minus the cosine of n pi plus n. Sorry, plus pi. Plus pi. So now we can continue. So now we go the sum from n equals 1 to infinity, 1 over 2n. Cosine of n pi, well, that is n pi. Cosine of n pi plus pi, well, that's the same as cosine of n pi. This right here is the same as cosine of n pi, right? Since a negative cosine of n pi, because this plus pi is the same as cosine of theta plus pi. If cosine of theta plus pi, that's negative cosine of theta. So this part only is negative cosine of n pi. It makes this into plus, gives us 2 cosine of n pi. Yes, now the sum from n equals 1 to infinity of these 2's cancel out. We get cosine n pi over n. So now let's notice that cosine of pi is negative 1. Cosine of 2 pi is 1. Cosine of 3 pi is negative 1 again. So basically, this will alternate between negative 1, then 1, then negative 1, then 1. So this we can rewrite as negative 1 to the nth over n. Okay, now let's see what this is actually. This is negative 1 plus 1 over 2 minus 1 over 3 plus 1 over 4. And notice that this is the alternating harmonic series, but multiplied by negative 1. So you have 1 minus 1 over 2 plus 1 over 3 minus 1 over 4, da 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 da. So the value of this series is ln of 2. So this gives the value of our integral to be negative ln of 2. So why is this ln of 2? Well, we can use the Taylor series for ln of 1 plus x. So let's see how we get that. First off, we have the general geometric series, 1 over 1 minus x. This is the same as the sum from n equals 0 to infinity of x to the nth. Let's integrate this with respect to x. So we'll get ln, the absolute value of 1 minus x, minus is equal to the sum of x to the n plus 1 over n plus 1, and this is the sum from n equals 0 to infinity. So, and also notice that I have not put the c because it won't be needed. So now let's see, we have negative ln of 1 minus x. Well, since we want ln of 1 plus x, we'll let x equal negative x, and we'll have negative ln of 1 plus x. This is the sum from n equals 0 to infinity, negative 1 to the n plus 1, and then we have x to the n plus 1 over n plus 1. And this is going to become, if we put in 0, we're going to have negative 1. Let's see what a few terms are. So if we have n equals 0, we have negative 1 to the n plus 1, so that's 1. X, n plus 1 is again 1 over 0 plus 1, that's 1. Then we have negative 1 to the 2, x squared over 2, right? And this keeps on going. So we have negative x plus, this is squared, so we have x squared over 2. This goes on and on. Let's let x equal 1, then we'll have negative ln of 2 is equal to negative 1 plus 1 over 2, yada yada yada. And that is exactly the sum we had right here. So this shows that the value of our integral is in fact negative ln of 2.